All right, welcome back to part 2 of ARoD Autonomy and Control. So, gonna go over the stuff that I left out from last time, and part of that was the path following in our navigation stack. So, the type of control system that we used is called the Stanley Control Law, and what that is, it's a path following controller, and it's very similar to the standard PID control system. However, this one only includes the proportional P gain. So it's just a proportional controller. However, it uses two sources of errors to converge our robot onto a path line. And so the first one being the cross-track error, which is this perpendicular distance that the robot is away from the trajectory line that you want it to follow. And then also the heading error, which is the angular difference between the robot's heading angle and the pathline angle. And so this is the formula that we used. This formula we got from I believe, a online source for autonomous vehicles, and it turned out to be a pretty good algorithm to use. So I'm going to go over how we actually went about coding and finding the cross-track error. So if you guys remember the overall layout of our waypoints, where we had waypoint A as the first waypoint and waypoint B being the waypoint that we're trying to navigate to, and then point C is where the robot is currently at. So if we follow that same convention, first we have to calculate the distance between point A and B. And we do that using the same methods as before, which I'll quickly show you guys again. So that was this method where we use the curvature of the Earth and then the Haversine angle, and basically compute the, that gives us the calculated distance between the 2 points. So once we find that, that's this distance right here, then we have to find the angle between line A and C and A and B. So that's this angle right here. To do that, you have to use the atan2 function, which basically, I think what it does is it finds the angle of this line and the angle of this line, and then it subtracts the two, and that gives you your delta theta. And then from there, to get that perpendicular distance, you just take the sine of that delta theta and multiply it by the distance between A and B. And that gives you your cross-track error. And this error is computed every cycle, or every time the code is looped. This calculation is updated. The next thing is the heading error. So in order to do that, you basically read the current angle from your magnetometer, and then you subtract the desired angle. The desired angle is calculated based on the angle that the waypoints form. So let's say this is point A and this is point B. The code would pre-calculate that heading angle or desired angle, and then it would just have that saved in its memory. And then the current angle is read from the magnetometer. And then all you have to do is just subtract the two. And it's pretty simple. And then the heading, oh, need to change that, but to find the steering angle, because that's our control input to our system, is only steering angle. So to find that, we just follow the same equation that was shown before. Where you take the heading error and add the tan inverse of the cross-check error multiplied by the gain factor, and then it's divided by the velocity plus a softening constant. These two they were very important for us in terms of our robot, because this equation as a whole was developed for an autonomous vehicle that would have a wide range of varying speeds. So they would add this velocity and softening constant to basically change how the steering input is implemented when the car is going really fast or really slow. But for us, our speed was mostly constant, so it didn't really matter to us. However, the softening constant did play a decent role in how big the steering angle would change based on some of these errors, or the cross-check error mostly. Another like important thing was to make sure you watch out for what type of units you're using, because a lot of times in Python and probably in C++, when you compute the tan function or sine function, it gives you your it gives you the value in radians. So if you need your final value in degrees, like for us, we needed our steering angle to be in degrees because that angle would be fed into our servo, which only accepts degrees. You just have to try and make sure you keep that same standard of units. And so we used this degree converter to get that. So I uploaded our code right here, and it's in our ASME drive. So once you have your system completely done, a really, really important thing to do is to record your data. I found this out just through kind of trial and error, that recording data from all your sensors, all your calculated outputs, and your inputs is really important. So what I did was I created a data logging file, and I had the code, our main code loop, basically just printing to that file at the end of its computational cycle. So like in the while loop at the very end, I would have it just print to that file, all these data points. And what it does is it helps you troubleshoot your system. You can basically see everything that the robot is thinking. So all those like algorithms or equations that you put in, if you record the data of what's being calculated that goes into the equation and then what comes out, it really does help with just understanding like what went right or what went wrong. And then also I would try to create like a nice either like a MATLAB program or Python program that plots your data, because that also really helps with just understanding how well your control system functions. As you can see here, ours wasn't that great. It was decent, but not perfect. For the cross-check error, the blue line is uh, the desired error that we want to hit, and the red line is the actual values. You can see that it's very noisy, very spiky, and that's just due to either just bad calculations from the equations or uh, just noisy sensor data from the GPS. Same for the heading error. The blue line is the individual segments the of each waypoint and its desired heading. In this, you can also see that the robot was it was going near the right heading angle, but it was very like oscillatory and just kept going up and down. Um, and then there's a lot of large spikes this is where the robot would make a full 360 because it just got so thrown off of its course. And yeah, so this information showed us that our system in the end wasn't perfect. It still could have used a lot more improvements as far as the control system is concerned. And then also, it's good to have a nice map graph just to see the GPS points as well, overlaid on top of the desired path. Um, Another nice thing that we forgot to show is we did make a graphical user interface. This is pretty nice. It helps with remote control of the robot. The way we had ours interfaced was directly from our computer um, to the Raspberry Pi on the robot. And it was nice because it lets you like just quickly launch these certain commands by just clicking these buttons. And yeah, just a nice little interface. It's something that we could look into as well. So I'm going to talk about the hardware that was on our robot. Um, so we had a Raspberry Pi, which they consider it as a single board computer, not so much a microcontroller, but more of a computer. And what we had it doing was high level navigation and control. It read all of the sensor data and computed them, and then fed that information to the microcontrollers. So the Raspberry Pi would read the GPS data, the IMU data, and the LiDAR data, and it would determine which direction to steer. And it would feed that information to the Feather M4, which had direct control of the drive motors and the steering servo. And the Raspberry Pi would tell the Feather which direction to turn and also when to turn on the drive motors or turn them off. And the purpose of this was that the microcontrollers help reduce the computational loads and also avoids timing issues from driving motors. So I guess microcontrollers are better at doing PWM type of signaling for motors. And they also have a more like robust compute or processing speed or power. when it comes to simple tasks like driving motors or servos, whereas with the single board computer, sometimes the CPU can get, I guess, overclocked, I think, and it might be processing so many things at once that it doesn't have enough like bandwidth to also account for driving a motor or servo. So a lot of times this is what people do is they split the computational load from the single board computer with a microcontroller. So that's what we decided to do. We also had a Arduino Uno that would read ultrasonic sensor data. The reason for this was that we were having a lot of trouble interfacing with the ultrasonic sensors. They used to be attached to the Raspberry Pi, but the coding libraries for it just weren't as robust as the Arduino coding libraries. And so we added this Uno just to interface to that, and then it would just feed the sensor data to the Raspberry Pi. And then we also had an Arduino Mega, which would just display eye animations on LED panels. So if you guys watched that YouTube video on flight computers versus flight controllers, I tried to relate this to that guy's explanation. So the Raspberry Pi is considered as the outer loop because it was running multiple processes at once, and it also had a pre-planned mission loaded into its code, which was the list of waypoints and the for loop that iterated each of them. And the feather is considered as the inner loop because it basically drives the motors and keeps them going while it's waiting for the Raspberry Pi to give it new commands. So it's very similar to how the feather is almost like the flight controller, where it would stabilize the drone. In our case, it wasn't really stabilizing the robot, but it kept the robot moving forward, and it kept it steering properly. And then the Pi would just give it new commands on which direction to go. So I was thinking of a possible design for us that we could try to use. Working with the Raspberry Pi, it was pretty simple and straightforward, even having no experience doing it. So I'm proposing that we could use a Raspberry Pi as our flight computer, where it can interface sensors like a GPS, a LiDAR, a camera, an IMU, and it can give commands to an Arduino Uno, which could act like our flight controller. And then this Uno would interface to the electronic speed controllers, which connect to the motors. Doing it this way, I feel like we could we'll have the ability to connect more sophisticated sensors like cameras and lidars, and then we can run more complex algorithms like machine learning, computer vision, and SLAM. And we also can try to use ROS, which provides many like coding libraries and just robotics programs for just building more complex robots. And also the Arduino has a nice fast processing speed. And also it's pretty easy to code, and there's most likely many examples online for how to build a flight controller out of an Arduino Uno. And then there's a lot of easy interfacing between the Pi and the Arduino Uno, where you could use I2C or serial USB interfacing. And then this is another variation of that last design, but with the Raspberry Pi, we can either code in Python now, or we can also just stick to C++. And then instead of just using an Arduino Uno, we might be able to use a off-the-shelf flight controller, like the ones that you would see on a commercial drone. And I think that we could interface between those two. And so that would change our coding to being either, if we use the Arduino Uno, we would have to code in C++. And if we use the flight controller, we wouldn't have to do any coding, which would be pretty nice. And then also I added these two boxes right here. This would be our multiplexer, which would basically have direct control over the flight controller, where the two inputs could be a remote control or the Raspberry Pi. And so this type of setup would allow us to have sort of a emergency like an emergency remote control type of setup, where if the drone is going way off course, we can just turn on the remote control and then take over the flight of it in case something goes wrong. Yeah, that is all I have for the rest of the presentation. So if you guys have any questions, just let me know.
Yeah, Antonio?
Yeah.
This is because I'm not familiar